Okay. Last time, we discussed two sequences. The first one was En, and the second one was Fn. And we know that this guy. Sorry. This sequence is converging to so-called Euler's number, and also at the same time, we were also able to prove that this was a decreasing sequence. So yeah, and En is always less than equals to Fn, right? And En is increasing and Fn was decreasing, and all these numbers, they were satisfying these inequalities. And well, and E1, E1, E2, E3, so sequence En is increasing, but it can never exceed, for instance, like F1. So En is increasing, but bounded by this number. So, in fact, any of these numbers, but. So this is converging sequence, which is called the Euler's number, which I will say E. But likewise, the another sequence, F, they were decreasing sequence, but they can never be lower than E1. So Fn is decreasing but bounded below. So therefore, by the monotone convergence theorem, so this is convergent. And I say this number is F. And we all know that this number is Euler's number. But what about this guy? And I say that this number is in fact the same as this guy. We're going to prove that by taking the difference between Fn and En. So Fn is always slightly greater than En. So Fn minus En is always greater than 0. And this is Fn. And this is En. Times 1 plus 1 over n minus 1. The first factor is En, and the second factor is just 1 over n. Okay, so I just ended up with this equation, but I somehow want to find the upper bound of this. So this sequence is always less than equals to the first term of the sequence f. So this is less than f1 times 1 over n. But what is f1? So if I plug in n equals to 1, then this 1 plus 2 to the second. So is 4 over n. Okay. So Fn minus En, so they are greater than 0 and less than some constant multiple of 1 over n. So by the squeeze theorem, Fn minus En which is F minus E, but this sequence should converging to 0. So therefore, F and E, they are the same. It turns out to be the same number, right? So that means this sequence, this decreasing and bounded below sequence, will also converging to the Euler's constant. Okay, good. Let me digress a little bit. Whenever we say the Euler's number, then we always regarded it as a limit of this sequence. But there is another alternative definition of the Euler's number. And in fact, one of our homework exercise, it is suggesting you to prove that the Euler's number E turns out to be 1 plus 1 plus 1 over 2 factorial and 1 over 3 factorials and So from n0 to infinity, so 1 over n factorial. So, well, so this time the Euler's number is defined not by using a sequence, but by a series, this infinite series. Yeah, so this is so interesting exercise. So, well, if you have enough time, then maybe I challenge you to try this exercise. And once you're done this exercise, then, and if you have still enough time and you can still, interested and focus, then maybe you can try to find the Wikipedia page then. It is trying to prove that by using this identity, and it is trying to show that why the Euler's number must be irrational number. The proof is so easy and beautiful. The proof was actually invented by the famous Professor Fourier. So, I guess that is the first attempt that Euler's number is the irrational number. And being able to prove any given number is irrational or rational is, it actually turns out to so complicated task. Okay, anyway, all right. So this is the end of the chapter 1, and we are going to move to the chapter 2. Chapter 2. The functions and continuity. I guess the continuous functions, they are the protagonist of this freshman calculus discourse, the freshman calculus. Why? Because every single university, they are teaching, for freshmen, they are teaching the freshman calculus. So no matter which university you go, but you are supposed to learn the calculus. Why? Why calculus is so important? Because, this is my opinion, but calculus is about the study on the changes. Everything changes. Like direction of the wind and your stock market, and everything changes. And whenever we talk about change, then the best mathematical tool to describe such a change is, I think, is a function. And there are two different types of change. The first change is the discrete change. So 1, 2, 3, 4. If your function value is some discrete number, the discrete thing, then we say this. I say this is discrete change. But in our case, the function is the change of function is not. So in our course, we are mainly interested in the non-discrete changes of functions. And speaking of that, we are supposed to think of not just any random function, but functions with reasonable behaviors. I mean, so if you're trying to build any kind of theory for completely random functions, then there is no such a theory. Because, if you can never expect the behavior of function, then you can never be able to build any kind of nice theory. So therefore, for this reason, we are going to restrict ourselves in some sort of nicely behaving functions. So that is a continuous function. So what is a continuous function? Continuous function is a function such that if my input changes a little bit, then output also changes a little bit, right? So this is a continuous function. But however, in order to describe the continuous function, then first we are gonna need a very well-defined, mathematically rigorous definition of the continuous function. So this is what we're gonna do for today's lecture. All right, but anyway, before we do that, I'm gonna give you the some terminologies. Function. So what is a function? The function is a mathematical machinery such that if you plug in some input, then it is going to produce some output under some certain rule. So that means this rule is so well defined. So therefore, no matter which one of us plugged in the number, but this mathematical machine is going to produce the same output. And the set D is called the domain of the function. 도메인이 한국말로 정의역이죠, 그렇죠? 예, 그렇게. And f of x is called the value, and the set of all values of a function is called the range. 제가 한국말로 하면 거기 range가 한국말로 치역인가요? 저 어렸을 때 그렇게 배웠는데. 정의역, 그다음에 공역, 치역, 그렇죠? 뭐 이렇게 배웠죠. 공역에 대해서는 안 나왔고, 공역은 우리가 코도메인이라는 말을 써요. 코도메인. 네, 그러니까 range는 언제나 코도메인의 부분집합이 되겠죠, 그렇죠? 그래요. 네. And the set of ordered pair, it is called the graph. Okay, good. And a function is bounded. That means if you can find some positive number, and if your function value lies between minus n to plus n, then we say the function is bounded. So in other words, your function should not go to plus or minus infinity, right? So then your function is bounded. And also, we say function is bounded away from zero. If there is a positive number such that no function value lies between minus p to plus b. So what does it mean? So intuitively, so if a function is bounded away from zero, then my function value cannot get arbitrarily close to zero, right? So for instance, like function 1 over x, this is not bounded away from zero, because in that case, the function value can get arbitrarily close to zero. Okay. Yeah. Okay. In picture, so if this is plus p, this is plus p and minus p. So the function must be so your graph cannot get into this region. So this is what I mean by a function bounded away from zero. All right. Okay. Now we are turning to the mathematical definition, rigorous definition of continuity. And the definition, yeah. Right. Finally, time to introduce one of the most notorious definition in the freshman calculus, which is the epsilon and delta argument. Well, If you're interested in mathematics, then maybe once in your lifetime, I guess you have encountered this definition. Well, but for now, since we are already introduced to the convergence of a sequence. Therefore, this definition would not be that complicated. Okay, all right. So let me try to read the line by line. So we say the function f is continuous at c if for any positive epsilon, you must be able to find another positive number delta, positive real number delta, such that satisfying the conditions given below. I would say the blah, blah, blah condition. So what is this condition? If the distance between x and c is less than by this number delta, then that guarantees that the function value f of x and function value f of c, the distance between f of x and f of c is less than epsilon. So x different from c. So if x lies in the region c minus delta and c plus delta, then f of x lies in the region between f of c minus epsilon and f of c plus epsilon. If this thing guarantees that, so for any epsilon, if you can find a delta satisfying this, then we say f is continuous at c. Okay. All right. Yeah. And well, I will try to rephrase this by using quantifiers for any epsilon. There is a positive real number delta satisfying the blah blah condition. So what is that condition? If x is x and c is less than delta, then f of x minus f of c is in epsilon. So in other words, for all x in c minus delta in this open interval, then f of x is in f of c minus epsilon to f of c plus epsilon. Okay. All right. So if you can find delta satisfies this condition for every positive epsilons, then you're good to say your function is continuous at the point. Okay. All right. Yeah. Understanding this definition just by looking at these words seems to be somehow very impossible task. So I will try to show you by an example. One example and one non-example. Okay, all right. This is C and this is f of C. And this is my function. And I am pretty sure that my function is continuous at this point. Okay, and I will try to verify this definition by using this example. All right. First, so I will choose some random epsilon, like this one. Yeah, I'm gonna say the length of this line segment is my epsilon. And I will make sure that for this epsilon, I can find such a delta satisfying this condition. Okay, since this is my epsilon, so this is f of c plus epsilon. And this is going to be f of c minus epsilon. And okay. And I am looking for the range of x, such that the function value at this interval lies in this interval. So in this picture, I think the length of this line segment from here to there should be my delta. Why? Because from my viewpoint, the length of this line segment is slightly shorter than the length of that line segment. So if I choose the length of this line segment to be my delta, then well, if my x lies in this interval, then for all such x's, then function values are guaranteed to lie in this interval, right? So therefore, I can say, for this epsilon, this one is my delta. So I was able to find one delta, right? Well, in principle, any positive number less than this should be can also be your delta. But for educational purpose, I say this is my delta. Okay. Okay. So I could find one. I could find one delta. Now, but that is not enough, because in order to say the f is continuous, then I can find such a delta for every single epsilon. And we were just done with just one single epsilon. So let's try another epsilon. Okay, this time I will choose the smaller epsilon. So if this is my epsilon, then this point is f of c plus epsilon. This is so f of c minus epsilon. No. Okay. All right. In this case, what would my delta be? I think the length of this line segment could be my delta in this case, right? Because if my x lies in this interval, then the function values for this interval is guaranteed to be in this interval, right? Okay, so therefore, for this epsilon, I could find another epsilon, another delta. All right, and I guess you're pretty convinced that, yeah, even though we just tried just two different epsilons, but I guess at this point we are pretty sure that you can find deltas for every single positive epsilons, right? So in this case, we can say the function is continuous at this point. Right. Okay, good. But I would also like to try another example that does not allow delta for some specific epsilons, like this. This is f of c, and okay, and this is c. And I would like to discuss why this function fails to satisfy the definition. Okay. Well, first let me try. This is my epsilon. The length of this line sigma t is my epsilon. Then this is fc plus epsilon, and this must be f of c minus epsilon. And in this case, I will try to look for the delta. Okay, yeah. I'm not too happy about my picture because that is skewed too much. All right. Now, what do you think your delta? What do you think your delta in this picture? Well, yeah, I believe the length of this line segment should be my delta in this case. So this is your delta. Yeah, I know this delta is incredibly small, but the point is, yeah, I can find one delta, right? Yeah. So that is, for this epsilon, yeah, this is I was able to find the delta such that for every x values in this range, my function value is guaranteed to be in f of c plus epsilon and f of c minus epsilon. All right, but okay. But this time I will choose even smaller epsilon. This is my epsilon. So this is f of c plus epsilon. This is f of c minus epsilon. Okay. Now take a look at this. What would your delta be in this picture? There is no such a positive delta, right? Because in order to be delta, then well, for the proper delta, then C minus delta and C plus delta, the image of C minus delta and C plus delta should be lying in this region. But in this case, well, this side of the region may be in this interval, but this side of the region can never be in this interval, no matter how small your delta is. But the image of C minus delta and C plus delta cannot be in the range of f of C plus epsilon and f of minus epsilon. Okay, so therefore, even though you are very successful finding your delta at for this epsilon, but you have failed to find such a nice delta for this epsilon. Now, and in order to say my function is continuous, then you must be able to find these delta for every positive epsilon, right? So because of this function is not continuous. Okay, because you failed to find such a delta for this epsilon. Okay, all right. 제가 이건 다이그레션이니까 잠깐 한꺼번에 할게요. 여러분 이 데피니션 그러니까 사람들이 이 데피니션을 왜 사용한다고 생각하시는지 모르겠는데 그러니까 어떤 사람들은 이 데피니션이 사용한 이유가 그러니까 사실 우리가 이게 arbitrary야 충분히 가까워졌을 때 이런 말을 사용하지 않고 이렇게 애매모호한 용어를 사용하지 않고 연속성이라는 걸 정의할 수 있기 때문에 사실 퀀티파이어랑 부등식으로만 이용해서 정의하는 거잖아요. 그렇죠? 그러니까 그래서 너무 아름답다. 그래서 좋은 데피니션이다. 이렇게 주장하는 사람도 있어요. 물론 그 말도 맞는 말인데 저는 사실 이 데피니션이 되게 훨씬 더 중요한 거기 공학적인 의미를 가지고 있다고 생각하거든요. 그러니까 이게 실질적으로 되게 중요한 게 뭐냐면은 우리가 여러분들 여러분들 분명 이런 생각하는 사람 있을 거야. 나 수학과 갈 것도 아닌데 굳이 이런 거 왜 배워야 되지? 싫은 사람 있을 거 아니야. 그치? 근데 이게 되게 중요한 게 뭐냐면은 우리가 어떤 실수값을 계산한다고 생각해봐요. 그러니까 이게 우리가 f of c라는 값을 이게 우리가 의도한 참값이야. 그걸 계산하고 싶어. 그런데 실제로 우리는 이 값을 정확하게 계산할 수는 없다. 왜 그러냐면은 우리가 함수가 잘 정의가 되어 있다 하더라도 우리 인풋 값이 이 입력 값도 실수잖아. 근데 실수를 우리가 완벽하게 정확하게 딱 입력하는 게 불가능하죠. 그렇죠? 그래서 x가 파이를 입력해야 되는데 3.14, 159, 265, 3 끝까지 무한히 입력할 수 없죠. 언젠가 딱 끊어야 되잖아요. 그치? 그러니까 입력값이 부정확하기 때문에 출력값도 부정확값을 할 수밖에 없는 거야. 그치? 실질적으로 그렇잖아. 그치? 그러니까 우리가 실제로 의도한 실제 입력값은 C고 실제로 원하는 출력값은 F of C라고 한다면은 실제 우리가 입력하는 값은 그러니까 우리의 입력하는 어림값은 X고 출력되는 어림값은 F of X야. 그치? 그런데 우리가 분명히 생각해. 우리가 실제로 원하는 값은 이건데 우리의 함수값의 공산 오차가 그러니까 예를 들어서 우리의 함수값의 공산 오차가 그래서 100분의 1 안으로 떨어졌으면 좋겠다. 이런 상황은 분명히 존재하겠죠. 그렇죠? 그러면은 뭐냐면 그 얘기가 뭐냐면은 실제로 출력된 함수값 fx와 fc가 100분의 1 안으로 떨어졌으면 좋겠다는 소리야. 그치? 그러니까 결국 이게 뭐냐면은 우리 이 정의가 얘기하고 있는 게 뭐냐면은 우리의 함수값의 공사오차가 엡실론이라면은 이 공사오차를 만족시키기 위해서는 우리의 입력값을 얼마나 정확하게 입력해야 되겠느냐. 지금 그 얘기를 하고 있는 거거든요. 그쵸? 그러니까 델타가 바로 그 입력값의 정확도야. 프리시전이라고 나오잖아. 예를 들어서 엡실론이 100분의 1일 때 델타가 10,000분의 1이라고 나왔다. 그럼 이게 뭐냐? 우리의 함수값의 이 공사오차 100분의 1 아래로 정확하게 계산하기 위해서는 우리의 입력값은 10,000분의 1, 즉 소수점 넷째 자리까지는 정확하게 입력을 해야 되겠다라는 것을 우리가 알 수가 있는 거지. 그치? 그러니까 이게 그냥 수학자들에게 뜬구름 잡는 상아탑에서 하하호 하는 소리가 아니라 실제로 되게 중요한 이야기예요. 그러니까 에러 어널리시스를 할 때. 그렇죠. 생각해보니까 그렇지 않아요? 그렇죠? 이거 되게 중요한 얘기예요. 네. 한국말로 하니까 편하네. 네, 그래요. 네, 그래요. 다시 영어로 넘어가서. 네.
시험이 필수 정책법인데 정의역에서 구간이 끊겨 있는 함수 같은 거 예를 들어서 상수함수 같은 구간이 있는데
네.
부분이 아예 정의되지 않아 버려요.
아, 정의역이 실수 전체가 아닐 경우에.
그건 또 연속 함수가 아닌데 엡실론 등식을 넘버버는 뭔가 연습성이 안 보여지고.
아, 그쵸, 그쵸. 그러니까 예를 들어서 이런 케이스 말씀하신 것 같은데 정의역이 어떤 이렇게 구간인데 양 끝점에서는 어떻게 거기
양 끝점이
네.
함수값이 같아서
네.
치역은 실수 전체 집합으로 정의가 되고 있는데
네.
정의역은 정의되지 않은 구간입니다.
아, 그쵸, 그쵸. 그런 케이스도 분명히 존재하겠죠, 그쵸.
그런 케이스에서는 분명히 보여주죠.
일단 학생이 말한 그런 함수가 뭐가 있을까 한번 생각해 볼까요?
저
예.
시계 방향이나 안시계 방향으로 90도 돌리는 거예요.
아,
그러면 정의역이 퉁 비어버려가지고
그쵸, 그쵸.
구간이 닫히는 구간.
그러면은 여기가 이제 정의가 안 되는 정의역이 여기는 합수값이 정의가 안 돼 있는 거네, 그치?
엡실론은 어떻게 잡아도 그 부분이 전부 다 차열이.
그런데 우리가 함수값이 정의가 되지 않은 구간에서 우리가 연속성을 논하는 게 과연 맞을까요? 저는 약간 일단 그 생각이 드는데. 아, 제가 학생의 질문에 제대로 대답하고 있나요? 잠깐.
무슨 말씀인지.
예. 혹시 잘 이해가 안 되시면 수업 끝난 다음에 어디서 같이 한번 또 이렇게 디스커션 해봐요. 예, 그래요. 예. 예. 아, 제가 사실 말귀를 잘 못 알아듣습니다. 그래요. 예. 아, 다시 영어로 다시 영어로 하는 척. 자, 그럼 영어가 왜 안 되지? 오케이. 어, 어. Okay, so we have very silly exercise, 3x plus 1. And I am supposed to show that this function is continuous at x is 3. Okay. All right. All right. To show that this function is continuous, then for any epsilon, yeah, if I can find such a nice delta, then we are done. But instead of trying to find such a nice delta, I will try something like the backward analysis, just as we did it for the convergence of a sequence. So that means I will try to find that under what condition f of x and f of 3 is less than epsilon. If I can answer the question, then maybe I can find the delta. All right. So f of 3 minus f of x minus f of 3 is, this is f of x, and minus f of 3 is 10, right? So this is 3x minus 9, absolute value. And this is 3 times x minus 3. And we require that this number must be less than epsilon, right? Now, can you guess under what condition this guy is less than epsilon? I guess this guy is less than epsilon if and only if x minus 3 is less than epsilon third, right? Aha. Now, this gives me idea what would my delta be. So that means, if my delta is less than this number, then I'm pretty sure that f of x minus f of 3 is less than epsilon. Okay, all right, yeah. So this is the proof for any epsilon we choose our delta to be just 1/3 of the epsilon. But this is still positive number, right? Then, so if now make sure that this delta is satisfying the blah, blah, blah condition. So if x minus 3 is less than delta, then f of x minus f of 3, which turns out to be the same as x3 minus x minus 3. And this 3 just carries over. And x minus 3 is known to be less than delta. But this is 3 times epsilon third, so which is just epsilon. So, so therefore, if I set this is my delta, then this delta is satisfying the condition. So x minus 3 is less than delta, then the function value f of x minus f of 3 is less than epsilon. So that means for this epsilon, for this epsilon, I could find the delta satisfying the condition. But the choice of epsilon was completely arbitrary. Therefore, I can say for every epsilon, then I can find delta. So the function is continuous. Okay. Yeah, and another silly exercise. Show that a constant function is continuous everywhere. Okay, so just like before, so under what condition the function value is less than function value and f of c is less than epsilon. So this is k, and this is also k, so equals to 0. Oh, so no matter what, f of x minus f of c equals to 0. And clearly, this is less than epsilon, right? Because epsilon was already chosen to be some positive number. Okay, then what would my delta be? In this case, no matter which delta, no matter what, this inequality is satisfied. So therefore, I guess in this case, the delta can be any positive number. Any positive number will do, satisfy the blah, blah, blah condition. Okay, so for any epsilon, we let delta be any positive number. If x minus c is less than delta, then fx minus f of c, which is always equals to 0, and so satisfies the condition. Okay. So yeah, I know this is very silly. Well, anyway, but even though this is so silly, but well, for any epsilon, we were able to find the delta. So the proof is done. Okay. Okay, and now we are turning to the next section. Continuity at a point using limit. Just as we had the limit for the sequence, we also have the notion of limit for the functions. And the definition is we say the limit of function as x tending to c is L. So, well, we denote like this. And it's defined like this. For every epsilon, you should find a delta, positive delta, satisfying this blah, blah, blah condition. So what blah, blah, blah condition? And this blah, blah, blah condition looks almost identical to the previous definition, but only one difference. What is this? This, well, the condition will actually prohibit x from C. So x must be different from C. Okay. So using quantifiers, I should rephrase this definition like this. For any epsilon, there is positive delta satisfying the blah, blah condition. So what condition? So x minus C differs from C less than delta. But since we do not want x to be C, so the absolute value of x minus C should be strictly greater than 0, right? So I am putting one additional inequality over here. Thank you. Then f of x minus f of C is less than delta. Sorry, not delta. Epsilon. Oh, no, sorry. Yeah. I am confused. Epsilon. Okay. Which is the definition of oh, all right. All right. So it looks like these two definitions, they are almost identical. The definition of continuous function and definition of limit, they are almost identical, except for this. So it looks like I can give you another alternative definition of continuous of function. So alternative definition of continuity. F is continuous and x equal to C is defined to be if and only if sorry. Okay. Some of you might be wondering, what happens if x equals to C? So, the definition of continuity does not involve this inequality. But actually, if this guy is satisfied, then when x is then if this guy is satisfied, then for the punctured interval from from C to C plus delta and C minus delta to C, this implication, this condition is satisfied. And on top of that, if x equal to C, then f of x minus, well, then this L is now f of C. Then if x equal to C, then f of x minus f of C is automatically going to be 0. Therefore, this inequality is also satisfied, right? So writing like this is also can also be considered as a definition of the continuous at C. Okay. All right. Just one more thing to add for the limit of functions. So, well, since we do not want to consider to the case when x equals to C when we are discussing the limit. So that means the limit only cares about the neighborhood of the point C. So the behavioral function, the limit of function is only affected by the neighborhood of the C, but not precisely the point at C, right? Okay, all right. Now, for the rest of today's lecture, so we want to consider the relations between the convergence of the CX sequence and the continuity of a function. Suppose that f is continuous at point C. Then, for every sequence that converges to C, the sequence FAN converges to f of C. Okay. We have a continuous function at C. Now, we consider a sequence that is converging to C. Then it says that this is a newly defined, newly obtained sequence. So by taking composition with the sequence with the function. So this is new sequence. And this new sequence always converges to the f of C. Okay. This is the proof. Number one, f is continuous. Okay, all right. So why is that? The first, since f is continuous at C, so that means for every epsilon, there is a delta such that if x minus C is less than delta, then f of x minus f of C is less than epsilon. Okay, good. And also, the sequence is converging to C for any epsilon, there is positive integer n such that if index is greater than n, then an minus C is less than epsilon. So we have these two conditions. Now, what I want to do is I have to just combine these two conditions so that I can prove that this guy is converging to f of C. All right. So choose any epsilon. Now, okay, choose any epsilon. Oops. And since f is continuous at this point, Therefore, for this given epsilon, then I can find a delta satisfying this blah, blah, blah condition, right? So since f is continuous, there is a delta satisfying the blah, blah, blah condition. Okay, now this is interesting. Now for this delta, this delta is still some positive real number. So now what I'm going to do is using this delta to be the epsilon for this condition given in this definition. Now for this delta, but since this delta is still positive number, then I can still find another positive integer n such that if n equals to this large n, an minus c is this time around not less than epsilon but less than delta, right? So for this delta, there is another positive number n such that if n is greater than this, then an minus c is less than delta. Okay. Now this number an is in the interval from c minus delta to c plus delta. So if you plug in this number towards your function f, then fan and minus f of c should be less than epsilon, right? Why? Because this delta is known to be satisfying this condition. So for any number that lies in this interval, so it must satisfy this condition, right? So therefore, if you replace this x by an, but then this inequality must be also true, right? All right, okay, yeah. But anyway, let me summarize this. For any epsilon, okay, so we can ignore this part. I was able to find a positive integer n such that if n is greater than n, then fan minus fc is known to be less than epsilon. So this proves that the sequence is converging to f of c. Okay, good. Okay, well, in fact, this condition, so every continuous function is, well, I would like to rephrase the theorem like this. If your function is continuous at the point, then your function is respecting the notion of the convergence of the sequence. Well, if your sequence, suppose that you have a sequence in the domain of a function converging to the point C, then composing with the continuous function, then you're going to get another sequence in the codomain in the range of your function, and then the newly obtained sequence in the range of a function is still converging to the point. So I say that if your continuous function is respecting the convergence. And actually, this condition, it turns out to be the characteristic property of the continuous functions. The converse of the statement is also true. I have a continuous function. Sorry. Okay. This is just a function defined on an interval containing C. So suppose that I have some random function whose domain contains some interval that contains C. Now, and we still do not know this function is continuous or not. But suppose that this function is satisfying this nice property. If any sequence is converging to point C, then the composed sequence is also converging to f of C. Well, in other words, this function is also always preserving the convergence. So I have function satisfying the condition. So then f must be continuous. So what is this? Take a close look of this statement. Well, the previous theorem, well, if your function is continuous, then your function preserves the notion of the convergence from domain to codomain. And in this statement, if you have a function that is preserving the notion of the convergence from domain to codomain, then it says that my function is continuous. So in this sense, I can say, aha, this is some sort of the converse of the previous theorem, right? Okay, yeah. Now, I want to prove this. And the proof of this is one of my favorite in today's course, in today's lecture. Why am I trying this? Why am I trying to prove this? Even though this is not the part of the textbook. Because showing the proof of this, I can try to negate the definition of the continuous of a function. I will try the proof of this by using the proof by contradiction. Suppose not. So what does it mean? Yeah, I have a function satisfying this nice property, but even in that case, let us suppose the f is not continuous at this point. Then I want to derive some kind of contradiction. So assume that f is not continuous at C. Okay, all right. Okay, it's time to take a negation of such a mathematically compound statement. Okay, so let me try to remember the definition of continuity. So that is, for any epsilon, if you can find delta satisfying the blah, blah, blah condition, then we say the function is continuous. So therefore, the negation of that is there is one very special F positive epsilon. For that epsilon, you can never be able to find delta satisfying the blah, blah, blah condition, right? That should be the negation, right? So that is for there is very special epsilon. Yeah, I will call the epsilon 0. And for this epsilon, you can never be able to find such a nice delta. All right. In other words, that means for all positive delta, the negation of the blah 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 statement is also true, right? This symbol implies the negation of the statement. Yeah. All right. So for this given epsilon, yeah, sorry. Then for every positive delta, the negation of this blah blah statement is true. So this is going to be the negation of this whole definition, right? Okay, so what I'm supposed to do is, I'll try to find, well, the negation of this implication. Do you know what is the negation of the implication? Yeah, okay. So, 여기 한국말로 할게요. 여러분, A이면 B다의 논리적인 거의 부정형이 뭐예요? A이면 B, 혹시 그런 거 배웠어요? 그쵸. 예를 들어서 내일 해가 서쪽에서 뜨면은 내가 여러분들의 전부 다 뭐 10억 원씩을 드리겠다라고 약속을 했다고 준다. 약속. 그 임플리케이션이잖아요. 그치? 근데 내가 거짓말 제기할 수 있는 유일한 케이스가 뭐야? 내일 해가 서쪽에서 떴음에도 불구하고 여러분한테 돈을 안 주면 내가 거짓말 제기가 되는 거지. 그치? 그러니까 A이면 B다의 부정형은 뭐냐면은 A이고 not B이다. 그치? 그게 부정형이겠지. 그치? 그러니까 이건 뭐냐면은 이고 이거겠지. 그렇죠? 이거 부정형이 사실 이게 약간 학원 선생님처럼 말하자면은 사실 부정형 같은 거 시험 문제 되게 단골 문제거든요. 이제 중간고사. 그래서 한번 강조하느라고 한번 말씀드렸어요. 예. 그렇죠? 그러니까 이게 뭐냐면은 생각해 보면은 그러니까 이 말은 뭐냐면 이거 니게이션 하기 전에 이 괄호 안에 이것만 생각해 보면 이 C 마이너스 델타 C 플러스 델타 범위 안에 있는 모든 x에 대해서 요 분수식에 만족한다는 소리잖아요. 그치? 그러니까 요거의 부정형은 뭐냐면은 C 마이너스 델타에서 C 플러스 델타 사이에 있는 x 중에 어떤 특별한 x가 분명 하나 존재해가지고 요 분수식이 만족된다는 소리겠지. 그치? 그치? 그러니까 그래요. 그래서 어떤 엡실론 제로가 존재해가지고 이 엡실론 제로에 대해서는 우리가 어떠한 델타를 잡든지 간에 델타가 아무리 작아도 어떠한 작은 델타를 잡든지 간에 이 범위 안에 요 괴상한 친구가 한 명이 존재해가지고 이 괴상한 친구는 언제나 이 분수를 만족해야 되는 거야. 그치? 이게 부정형이겠죠. 그쵸? 그래요. Okay, all right. So I guess we are all agreed to the negation of the statement. It's time to give you the definition of the proof. All right. So all right. Since we are assuming that my function is not continuous at the point, so there must be such an epsilon zero, right? Now for this epsilon zero, then no matter how small my delta is, yeah, this condition must be true. So that means now, so that means if I choose my delta to be just 1 over n, here n is some positive integer. If my delta is 1 over n, then I can still, well, this statement must be also true, right? For this delta, this one must be true, right? So that means for this delta, I can find some point in this interval satisfying this inequality, right? There is a point in C minus 1 over n and c plus 1 over n point x, such that fx minus f of c is greater than or equal to epsilon 0. Okay. We let this number x to be an. Why n? Because this n, well, this point x is obtained by choosing delta equals to 1 over n. So I call this number to be an. Well, and you can do this, you can find this number an for every positive integer n. Well, I mean, if n equals to 1, then you can find the point, and if n equals 2, you can find the another point. If n equals 3, then you can find another point, a3. So So continuing like this, you can construct a sequence a1, a2, a3, an infinite sequence. So we constructed, we have just constructed a sequence an, and this sequence an is satisfying these two conditions. First, since an is in c minus 1 over n and c plus 1 over n, right? So this means an minus 1 over, an minus c absolute value is less than 1 over n, right? And this sequence is also satisfying the second condition. Well, and this an is always satisfying this inequality, right? So fan minus fc is greater than equals to epsilon 0 for all n. Right? So we were able to build this very weird sequence. Okay, but existence of this sequence is guaranteed by this assumption. F is not continuous at C. Right. Okay, now why is it a contradiction? Because of the condition number 1. The limit of this sequence is C. Right? Right? Yeah. But the limit of this composed sequence can never be able to be f of c. Why? Because of this condition number 2. This composed sequence f of an can never get close to f of c by this much. Right? So this guy can never be f of c. And this is clearly the violation of this hypothesis. What hypothesis? We said the function is satisfying this property. Is fn is converging to c, f of an must be converging to f of c. That was the assumption given. But even though this guy is converging to c, but this sequence, the composed sequence, is not converging to f of c. And this is contradiction, right? Okay. So therefore, continuous function always carries the sequence convergence function to another convergence function. And that property is going to be actually the characteristic property of the continuous function. Yeah, I guess this is for today, and see you next time.